How much does it cost to build a space telescope? The answer is $10 billion. That might sound unbelievable, but that is the actual cost of the James Webb Space Telescope. And that price tag is absolutely worth it, because its observational capabilities are 100 times greater than those of the Hubble telescope. On the 25th of December 2021, after delays spanning nearly 15 years, the Webb telescope finally launched from the European Space Agency's base in Kourou. As the pinnacle of current human technology, its observational power exceeds our wildest imagination. Perhaps you, watching behind your screen, share the same questions I did. What makes the Webb telescope so amazing? And where exactly did those $10 billion go? In today's video, let's embark on a journey into the legendary story of the James Webb Telescope. Let's pull the timeline back to the 1990s. After the Hubble telescope achieved its initial successes, humanity began to realize the unique capabilities of space telescopes. To ensure a successor was ready before Hubble retired, NASA began planning a new telescope project early on. The original budget was $500 million. Although that was $500 million in 1995 money, everyone understood that this amount was nowhere near enough to build a space telescope. After all, its predecessor, Hubble, cost over $4 billion for construction and operation. Because of this, Webb's budget climbed steadily, eventually reaching that staggering $10 billion figure. The launch date also slipped from the originally planned 2007 all the way to 2021. During the 15 years that Webb was delayed, NASA continued to repair and upgrade the Hubble telescope, which is the only reason it is still working today. So, since Hubble can keep working, why did we need to develop Webb? The first reason is that Hubble's hardware is severely aging. Its last service mission was in 2007, so its current state isn't optimistic. It frequently suffers from glitches and crashes, and no one knows exactly how much longer it can function. The second reason is that they are fundamentally different types of telescopes. Hubble is a visible light telescope. To put it simply, the photos it takes are similar to what our eyes see, just capable of looking much further. Webb, however, is an infrared telescope. It can see things we cannot see, but it actually cannot see visible light. Therefore, Webb's primary mission is to search for the light from the very first stars and galaxies formed in the universe after the Big Bang. This sounds incredible, because our universe was born 13.8 billion years ago, and those first stars no longer exist. However, the light they emitted still remains in the cosmos, and through Webb, we might be able to observe it. This helps us immensely in studying the formation of the universe. It was designed as an infrared telescope because those first stars are so far away that their light has stretched into infrared wavelengths by the time it reaches us. It is worth noting that the James Webb in the telescope's name refers to NASA's second administrator. Webb led the U.S. through its earliest manned spaceflight programs, including Project Mercury and the Apollo lunar missions. The New Generation telescope was named in his honor. Now, the most expensive and critical part of building a space telescope is its primary mirror. Its main function is to reflect faint infrared light from the universe into the internal sensors for imaging. To achieve better results, Webb's mirror diameter reached 6.5 meters. However, if a mirror that large were made as a single piece, no launch vehicle in existence could carry it. So, NASA decided to design it as a foldable mirror composed of 18 hexagonal segments. Hexagons allow for excellent folding capabilities and superior stability, allowing it to be folded up for launch. Furthermore, the polishing error of these 18 mirrors could not exceed 10 nanometers to ensure the surface was extremely smooth, providing clear, high-resolution images. Such a massive mirror can withstand neither extreme heat nor extreme cold, and since the rocket launch generates immense vibrations, it required highly advanced protection, making the mirror assembly very heavy. To reduce weight, scientists chose a very light metal to build the mirrors, element 4, beryllium. Beryllium is a rare element in the universe. In nature, it is usually found combined with other elements in minerals, like aquamarine and emeralds. It has high stiffness, thermal stability, and thermal conductivity, making it perfect for spacecraft. Although beryllium is naturally grey, the mirrors look golden because they are coated with a thin layer of gold, only about 100 nanometers thick. This maximizes the reflection of infrared light while reducing absorption. Additionally, behind this giant mirror, there are 132 micromotors to position the segments. Each mirror segment has 7 motors attached to it. They adjust the mirrors with an accuracy of 10 nanometers. Since Webb needs to unfold in space, without these high-precision motors, it would be impossible to focus the light. If you look closely, you might notice a device resembling a receiver in front of the telescope. This is actually another mirror. When the primary mirror receives information, the light reflects 4 times before finally entering the instruments behind the main mirror. Actually, most of the instruments are located behind the mirror. The most important one is the near-infrared camera. It uses 4 sensors, each with a resolution of 2K. Near-infrared is the type of infrared light closest to red light, just beyond what the human eye can see. The sensors themselves aren't particularly unique, but the mirrors in front of them are full of black technology. We know that a standard camera usually has 1 shutter. However, in front of these 4 sensors, there is an array of 240,000 microshutters. This means each sensor has roughly 62,000 shutters in front of it. Each shutter measures 200 by 100 micrometers and can be controlled individually. This design exists because the area Webb observes is often very narrow and distant. If we want to observe a specific ray of light, we need tiny shutters to frame the image. Otherwise, the angle would be too wide, like a wide-angle lens, making observation impossible. Aside from the near-infrared camera, there is also a mid-infrared instrument. It detects longer wavelengths, meaning it can see even more distant galaxies. When a beam of distant cosmic light enters the main mirror, the internal system begins a series of complex operations. First, mirrors and filters split the light into different wavelengths, then adjust the size to distribute it onto the sensors. Webb's mid-infrared camera has a key feature. It is incredibly sensitive, capable of capturing the faintest light. This requires it to operate at a low temperature of -267 degrees Celsius, which is only 6 degrees above absolute zero. Why is this necessary? As we know, every object in the universe generates thermal energy. Some emit this as visible light, but most objects emit massive amounts of infrared light. Moreover, the Webb telescope itself generates heat and infrared light, which would be fatal for the sensitive mid-infrared camera. Cryogenic cooling solves this problem. To achieve this, NASA first launched it to the second Lagrange point, L2, 1.5 million kilometers from Earth. This is a gravitational balance point. Simply put, when Webb is here, the gravity of the Sun and Earth pulls it equally, keeping it balanced in position. The temperature at L2 is naturally as low as -220 degrees Celsius. Furthermore, beneath Webb lies a massive 5-layer sunshield, always facing away from its observation direction. When these sails unfurl, they block infrared light from the Sun and Earth, dropping the temperature to -234 degrees. But that wasn't enough. To cool it further, NASA installed an internal cooling device. It uses 2 pistons moving back and forth to compress helium gas into a pulse tube, generating a low-frequency sound wave of about 30 Hz. These sound waves travel down the tube. At the end, they compress, creating a high-pressure zone, and when they bounce back, they expand, creating a low-pressure zone. Don't underestimate this device. When the output sound wave frequency is synchronized, it creates a standing wave inside, keeping the high and low pressure zones in fixed positions. By tripling the frequency, the tube creates multiple high and low pressure zones. Since temperature and pressure are linked, this creates multiple hot and cold zones. By adding 3 heat exchangers made of thin metal plates, the heat is extracted and dissipated, while the cold is drawn out and sent to cool the sensors. However, this only brings the temperature down to -256 degrees. To finish the job, scientists installed another heat exchanger and a tiny hole less than 1 millimeter in diameter. When the cooled helium passes through this hole, it triggers the magical Joule-Thomson effect. The gas undergoes compression and then rapid expansion, causing the pressure to drop and the gas to cool instantly. This is the same principle as when you breathe out. Huffing with an open mouth feels hot, but blowing through pursed lips feels cold. Through this series of operations, the temperature is finally cooled to -267 degrees Celsius, the exact temperature required for the mid-infrared camera. It is hard to imagine that sound can be used for cooling. You have to admire the scientists' ingenuity. It is no exaggeration to say that the Webb telescope represents the highest level of human technology. That is exactly why its budget kept increasing during development, reaching $10 billion. Furthermore, Webb's location, 1.5 million kilometers away, means it cannot be repaired or upgraded like Hubble. To ensure its performance and reliability, massive amounts of testing and verification were conducted over the years. Even a tiny mistake could have meant $10 billion wasted. With the space shuttle retired, NASA ultimately chose the European Space Agency's Ariane 5 rocket for the launch. On the 25th of December 2021, Webb lifted off successfully. After a month of flight, it arrived safely at the L2 point. Then, on the 12th of July 2022, U.S. President Biden personally revealed the first full-color image from the Webb Space Telescope. This was Webb's first deep-field image, showing the galaxy cluster SMACS 0723, located 4.6 billion light-years away. Every speck of light in that image is actually a massive galaxy. The most distant one is a faint red dot, located about 13.1 billion light-years away. In other words, we are seeing it as it was 13.1 billion years ago. In the images taken by Hubble, this galaxy was completely invisible. Subsequently, Webb released many more cosmic images. Not only were they incredibly clear, but they also allowed people to witness the magnificent beauty of the universe. However, the photo that stunned scientists the most was taken in January 2024. In the top right corner lies a star system named JWST-140. It is currently the most distant galaxy ever discovered by humanity. Its redshift reached 14.32, placing it about 13.5 billion light-years away. It existed just 290 million years after the Big Bang. The light it emitted traveled for 13.5 billion years before finally reaching Webb's lens. This is one of Webb's primary missions, to search for early galaxies, study their formation and evolution, and even search for extraterrestrial life. You might be wondering, since Webb is 1.5 million kilometers away, how does it send these photos back to Earth? Webb actually carries a 68 gigabytes solid-state recorder, often cited as having about 60 gigabytes of usable storage, and it can transmit about 55 gigabytes of data to Earth daily. That sounds like a lot, right? But actually, the raw size of full-resolution images is massive. For example, the full-resolution image of the cosmic cliffs in the Carina Nebula is as large as 129 megabytes. Additionally, Webb was designed with a lifespan of only 5 years, though NASA hopes for 10. This is not just because it cannot be serviced, but because the propellant it carries will run out. Although it sits at the L2 point, it still needs to orbit that point to gather enough solar power, requiring fuel to maintain its station. But we shouldn't feel regret over Webb's short lifespan, because NASA is already designing the next generation of space telescopes. Its name is the Nancy Grace Roman Space Telescope. It is named after NASA astronomer Nancy Grace Roman, who is known as the mother of Hubble because she was instrumental in planning and designing the Hubble telescope. The Roman Space Telescope is expected to launch by 2027. Perhaps it will become a neighbor to the Webb telescope, and we look forward to its performance. Humans are small, confined to living on Earth. We often sigh at the vastness of the universe and the infinity of space-time. But it is precisely the emergence of these space telescopes that refreshes our understanding of the cosmos. Perhaps we will never leave the solar system to explore every corner of the universe personally. But through these telescopes, we can glimpse the laws and mysteries of the universe. The Hubble telescope showed us the charm of the cosmos and revealed the speed of the universe's expansion. The James Webb Space Telescope goes further, helping us understand the formation of galaxies, the evolution of stars, and the birth of planets. They are like humanity's eyes in the universe. Through them, we can trace back the past of the cosmos, and in doing so, better reflect on our own existence.